Today we're going to take a look at section 6.3, and we have been looking at rational numbers, and for the most part in this section we've been looking at fractions, right? And in the last section in 6.2 we were looking at adding and subtracting those fractions, and then in 6.3 we're going to look at multiplication and division. I want to talk to you first about the definition of multiplication and division. Multiplication and division with fractions is actually easier than addition and subtraction. Why? Yeah, you don't have to find a common denominator. So if you found a common denominator, it would be okay. It wouldn't hurt anything. It just would be more work, and it would make things need to be reduced more in the end. So we don't need any common denominators with multiplication and division, which makes it easier to work with. So when you're working with multiplication in particular is when we're starting with, and you have a over b times c over d, you simply multiply across the top and you multiply across the bottom. And I want to show you a diagram of why that makes sense, how that works. And we're going to use 3 over 5 times 3 over 4. And this is a rectangular diagram to show this feature. All right, so I'm going to draw a rectangle. And in my rectangle, I'm going to make it have, well, since I've drawn it wide, I'll make it have 5 vertical strips. So I'm going to divide it into 5 long pieces like this. They should look like they're equal. Mine are not very convincing, but just pretend for a moment. So where did I get the 5? Well, I got it from down here, right? That 5 down there. That's why I have 5. So in essence, I want you to visualize you're going to shade in 3 of those 5. Okay? So whatever you'd like to do to shade those in. Here's 1, 2, and 3. So I have 3/5 of whatever diagram you want. I'm using a rectangular region here. And then what I'm going to do is I'm going to split it long ways into 4 strips. And again, that's because of this number 4 down here at the bottom. So I'm going to split it long ways into fourths. There we go. I'm going to shade again. I'm going to use a different color so that we can compare these a little more easily. If you're doing it with a pencil or something with your working, just do the shading in a different direction. So instead of shading top to down, you're going to do left, right, or something like that. So I'm going to shade across the top here. Here's this column 2, or row 2, and here's row 3. Now, I'm going to use this diagram to talk about why the answer is what it is, and then I'm going to draw the diagram one more time to actually talk about how to really think about it in a more appropriate way. What you actually have here is a diagram where the answer is the part that's double shaded. Okay? So the answer to this is the 9 boxes that are over here double shaded in. Those were shaded both in blue and in red. So we have 9 boxes that are double shaded. And how many total boxes do I have in my diagram? 20 boxes. So that's one way to think about it, but it sort of leaves a little bit to be desired, because you're like, well, why is the answer the double shading? Why isn't the answer sort of everything that was shaded? What's really going on here? Well, if you think about it a little bit more directly, let me draw my diagram one more time. I want to shade in those same 4 rows to start with, or sorry, was it 3? 3 rows to start with. What I really want is of the original 3/5 that have been shaded in, that is of only the blue portions that are shaded in, I really want 3/4 of those pieces as my solution. So I really, if I'm really sort of looking at this from the right perspective, I'm only really dividing these pieces into 4s, because that's the only piece that I really have to start with. Okay, nothing's going straight. Pretend. All right, so those 4 pieces are the ones that I actually have 3/4 of them. So I really only have these 3 right here that are the answer to the question. It's 3/4 of the part I started with. Well, that's those 9 little boxes, and each box has size 1/20th of the whole diagram, which is why I did the picture like this to start with. It's much easier on the first picture to say, yep, there are 20 boxes. Whereas down here, it sort of looks like I'm missing how these pieces were divided up, the missing pieces, to get my full 20 boxes. I don't care which version of this you like best. They're virtually the same thing. They're just thinking about it from a little bit different perspective. Yes, Beth?
I was just thinking, like, I don't know if this is going to confuse you, but, like, if you do add all the shaded,
Mm-hmm.
it would be 18 over 20, right?
Okay.
Simplify that. You
You get 9/10. Yeah, you'd get 9/10, so it would be a different answer.
Okay.
And it wouldn't always match up to even being reducible in that way.
Okay.
It just depends on the numbers you're working with. Yeah. All right, so either way you do it, you're looking at the double shading, but you're thinking about it from a different perspective. I normally just present this picture, but I think it sort of leaves a little bit to sort of be thought through about what's going on for real. What's really going on is that I have 3/4 of the original blue diagram that I'm looking at. And that's where that actual piece is coming from and why I'm only counting those 9 blocks. Does that help a little bit? It's a rectangular diagram. There's nothing special about the rectangle except that it's easy to divide it into rows and columns. I mean, you could use circles and whatever too. It just doesn't visually divide as easily. So, all right. Multiplicative inverse and identity, or identity and inverse. The identity is simply a number that when you multiply, and that multiplicative identity is a number that when you multiply it by anything else, it doesn't change the value. So the number 1 has the property that when you multiply it by a over b, you get back a over b. And it doesn't matter if the multiplication is before a over b or after a over b, because actually we have a property that's called commutative, right? It says the order of multiplication doesn't matter. But the result, no matter how you do it, is simply that it's the a over b you started with. It is a number we multiply something by that doesn't change the value. And then the inverse is actually the value that we would multiply it by to get back to 1. And you guys know this property because you've used it many times when you've solved equations. So if you wanted to know what is the inverse, the multiplicative inverse of 4 over 5, what would it be? 5 over 4. So if I were to take 4 over 5, the question is what would I need to multiply it by to get back to 1, and it would be 5 over 4. You have another name for what we just did to that second value. What did we do to get from the first value to the second value? We made the reciprocal. Very good. So the reciprocal is this idea of taking the fraction and sort of flipping it, turning it upside down. And we used the reciprocal to get that value. Now, the reason that value is the multiplicative identity, though, is not because it's the reciprocal. The reason that it's the multiplicative identity is because when you multiply it by its multiplicative identity, you get back to the number 1. So the reason that the 5 over 4 is the correct value is because 4 over 5 times 5 over 4 is equal to 1. Okay? That's the reason why that's the case. We have a couple other properties to look at. The distributive properties next. Everybody, for some reason, remembers the distributive property. I don't know what it is about that one that everybody seems to remember the name for and what it actually means. So the distributive property has this effect that when we multiply it by something, sort of think about it like this, that it distributes to each of the pieces. So that a over b gets multiplied by the c over d, and that a over b also gets multiplied by the e over f. And it works for any rational numbers, a over b, c over d, and e over f. We also have the multiplication property of equality. And what that says is if we have something equal to start with, that is if a over b equals c over d, then we can multiply both the a over b and the c over d by the same thing, and it won't change the value. And you guys know this to be true, right? If I had this written as 5 equals, and we'll write 5 but in a different way, just for fun, 15 over 3. They're the same thing, right? That it would be perfectly okay if I multiplied 5 over 4 as long as I multiplied 15 over 3 by 4. It doesn't change the value of either one of them. Well, it changes the value of both of them in the same way. Let's say it that way. So it changes both of the values in the exact same way so that they're still equal to one another. And we use that property a lot when we're solving equations, don't we? We're trying to sort of remove something from one side or the other of an equation. All right. A couple more, and then we're going to do an example. Number 3 is the multiplication property of inequality. It has 2 parts. It says that if I have the expression where a over b is is greater than c over d, and I have a positive number, If I multiply by that positive number on both sides, the inequality stays a greater than inequality. Right, so if I have 5 greater than 7, and I decide I'm going to multiply both sides by 1/2, well, then 5 halves is still greater than 7 halves. Now, that's not true, right? But if the first statement were true, the second one would be as well. Let me switch my 5 and 7 so that they make sense. Come on. All right. Oops, I did it again. All right, now the equation's true, or the inequality is true. So if 7 is greater than 5, then 7 halves is greater than 5 halves. However, the second statement actually says what? What's different about the second statement than the first statement? What was that? The sign is reversed. The final sign is what you're referring to, right, Hannah? Okay, so what's different in the first part that makes that final sign switch? Right, this value right here says that E over F is less than 0. What does less than 0 mean? Negative. This is what you know to be true, this idea that if I multiply both sides of an inequality by a negative number, it changes the direction of the inequality. And I actually would like to show you why that's true, because it always sort of feels like a trick when it comes up. Like, I just have to remember to do this, and you do, but there's actually a good reason why it actually works. So let's take the number -1, just because it's easy to work with, and do this. So if I do -1 times 7, what do I get? -7, and -1 times 5 gives me -5. Which one of those numbers is larger? The -5 is larger, and by larger I mean, you know, it's furthest on the number line to the right. If I were doing this on the number line, -7 would be further to the left and -5 would be further to the right. So the reason that inequality changed direction is because I actually changed the sign on those numbers. And changing the sign on those numbers has that effect, that it actually makes something that's large and negative a smaller number than the number that's large and positive would happen to be. I mean, it reverses that idea. All right, the last one, number 4, says that if I multiply by 0, what happens? I get 0. Okay, so it's a multiplication property of 0. All right, so what we're going to do on the next slide is we're going to actually use these properties to solve for x. And as we use the properties, we're going to identify what property we've used when we've used it. Okay? And you might be surprised at how many of them you use in a single step and did never even realize it before. So if my goal is to solve for x, what do I need to do? Okay, we could divide by 3/4. What's another way we could do that? Because I don't like dividing by fractions. It just looks... we could multiply by the reciprocal. Okay? So first of all, what allows us to do this? I'm going to multiply by 4/3 on both sides. That's the multiplicative. What did you say?
Identity inverse.
Something else before that? This is... Yes, this is the multiplication property of equality. Now, it's not specific to the 4/3. Any number I multiply by on both sides would give me would be a result of the multiplicative property of equality. Now, the fact that it's 4/3 is specific, right? We used 4/3 for a reason, and that's what you guys were already picking up on. All right, so why is it that we used 4/3 then? You guys were telling me before, so just tell me again. Right, we used it to cancel out the 3/4. And the fact that it cancels out the 3/4 is the multiplicative inverse property, right? So right here, the reason we chose 4/3 was because it's the multiplicative inverse. Now, the reality is that when I multiply 4/3 times 3/4, what does that give me? It actually gives me the number 1, doesn't it? Right? I mean, that's the result of, I mean, that's why I chose that, is because that gives me the multiplicative identity. But what happens when I multiply 1 times x? That just gives me x. And that is the multiplicative what? What property allows me to know that 1 times x is x? So You had no idea you were using so many properties in one little single step, did you? That's the multiplicative identity. Now we need to answer the right-hand side. What do we get, excuse me, on the right-hand side? 1/5 times 4/3 is what? 4/15. It is like proofs, isn't it? My goodness. Just never know when things are going to sneak back in, do you? So the answer is x equals 4/15. But there are three properties that we used of multiplication to get that to happen. The property of equality, the property of inverses, and the property of identity. Crazy, huh? If you thought it was crazy, what about this one? What about this one's going to make this more complicated? There's a couple things, but one thing. There's addition. What else? Say again for me, Angela. There's addition and subtraction. We are going to have both features. That's true. And what? I have an x on both sides. Good. Anything else? The other thing that's kind of messy right now is the denominators aren't the same. That's a little bit unfriendly too. All right, so there's lots of ways that we could get started on this. Somebody give me a suggestion. Did you give me a suggestion? A common denominator. We could get a common denominator for everything to start with, couldn't we? I'm going to take it one step further, Hannah. I'm not just going to get a common denominator. I think I'm going to use the common denominator to get rid of all the denominators. Do you like that idea? Sound good? No more fractions? Anybody going to disagree with that idea? Okay, so I want you to look at the denominators I currently have. What would the common denominator be for all of them? 12. So what I'm going to do is I'm going to multiply both sides by 12. What allows me to do that? Yeah, that's the multiplicative property of equality. Now, I'm going to use that 12 along with what property next? Very good. This will be the distributive property because I need that 12 to multiply to every piece, don't I? So those red lines are representing that I'm using the distributive property of equality actually as well, since I'm working with an equation. All right, so what happens when I multiply 12 times 2/3? Okay, so one thing you could do is recognize that's 24/3. What's 24/3? It's 8. All of the solutions I'm getting are going to be whole numbers because I chose the common denominator to multiply by. So this is actually 8x on the very first piece. How about the second one? What's 12 times 1/4? 3. Very good. How about the x over 6 times the 12? That's 2x. And then the 1/2 times the 12 would be -6. Great job, guys. All good? Okay, now what do you want to do? X is on the same side, so which x did you like to move, Hannah? The 2x. How are we going to do that? Okay, what property allows me to subtract 2x from both sides? Something of equality, right? Do you remember what it is? Did you find it?
Like additive or subtractive?
Yeah, this is the additive property of equality. The additive property of equality says I can add or subtract the same value from both sides. It won't change the value of the two sides. It'll keep, well, not it won't change it. It won't make them not equal. It will keep the two sides equal. That's the additive property of equality. Now when I do that, 8x minus 2x is a what? That's 6x. I still have the plus 3. 2x minus 2x is actually 0 minus 6. I know it feels really weird to write the 0 there, but why in the world did we subtract the 2x anyway, Hannah? because you actually wanted to move the x, is what you told me earlier, right? You wanted there not be to be an x on the right-hand side. So the reason we chose to subtract 2x is because 2x and negative 2x gave me 0, right? And that's what we wanted to have happen, is we wanted it to give me 0. Well, there was a property there. Why did we choose negative 2x? Well, we did it because that was the additive identity, right? The additive identity to 2x is negative 2x. That's why we chose it. Not only that, but we liked it because what happens when I do 0 minus 6x? I'm sorry, 0 minus 6. Yeah, I get negative 6. Why? Because that's the additive. Oh, I had the wrong one written down before. No wonder you guys are looking at me funny. That one was supposed to say inverse. Additive inverse, this is the additive identity. Additive inverse is what lets me choose the right one, and then the additive identity is what adds something and doesn't change it. Excuse me on that. But we have to do that exact same thing again to move the 3 now, right? So if I want to move the 3, what do I need to do? Subtract the number 3. And as I do that, I'm using two properties at the same time. I'll consolidate it this time to give me 6x on the left and negative 9 on the right. What two properties did I use? That was the additive, inverse, and the additive identity, right? The inverse is what told me to choose the negative 3, and the identity is what makes that turn into 6x instead of 6x plus something else. Last thing, what do I need to do? Divide by 6, and I'm going to write it a little bit differently just because it'll be easier for you to identify what we really did. I didn't mean a 3 there. Let's get that one right. I'm going to write down that I'm dividing by 6 as multiplication by the fraction 1/6. Why did we choose 1/6? Because why, Carrie? It's the reciprocal. And what identity tells us about the reciprocals? That is the multiplicative inverse. And we know then that the 1/6 times the 6 is actually going to give me the number 1, right? I'll finish the right-hand side in a minute. And then 1 times x is going to give me x. And what property did we use to get from 1x to x? Yeah, that's the multiplicative. Again, you have to specify you're doing multiplicative. It's the multiplicative identity. What happens on the right? Well, on the right here, I had negative 9 over 6. What does that become? Negative what? 3 over 2, I think, right? Negative 3/2? Yeah. So this is negative 3/2 because they both will divide by 3. Yes, Jana. It could. Yes, it could. You're going to have a couple in the homework that'll be like this too, so you'll have some practice to doing it, yes. You've got to recognize that you're using all of this mathematics. You guys have been doing it forever, right? You didn't realize there was so much involved in each step you were doing, did you? There really is. There's a lot involved in how you're making those decisions. You just didn't know it. All right. Multiplication. We'll turn into division a little bit here now. Division of rational numbers. This is a funny way to define division, at least in terms of what you've remembered probably. But the division of rational numbers says the following. If you have a over b and c over d, and you want to divide the first one by the second, it is equal to e over f, if and only if e over f is a unique rational number, such that it has this equality property. Again, let me do it in terms of numbers so you can see that this is exactly what you've used all the way along. I'm going to use whole numbers just because they're easier to work with, but it works with fractions the same. The reason that 6 over 2 is equal to 3 is because 2 times 3 is equal to 6. That is all this says. And that's exactly how children usually are exposed to division for the first time anyway. They say something like, what is 6 divided by 2? And the answer is going to be, well, what times 2 equals 6? Oh, it's 3, so the answer's 3. Okay, so this is all this definition is telling you. Now, this theorem down here, this algorithm down here, is actually telling you something else you've seen before, but probably never stopped to consider why it works. This is telling you that if you divide two rational numbers, it is equivalent to multiplying by the reciprocal on the second one. Do you guys remember that fact? I actually used it just a minute ago. I said, well, we could divide by 6, but instead I'm going to multiply by 1 over 6, right? I used that idea when I was doing that before. But I want to show you why it works, and we're going to do it with these abstract, weird-looking values, because I want you to see that it really works all the time. It's not something special to any numbers I'm making up. So if we had a over b divided by c over d, what I'm going to do is I'm going to take that a over b and c over d, and I'm going to write them in a division that it looks like with a division sign between them like this. So here's a over b over c over d. So all I did was take this division sign and write it as a big fat division sign between it vertically. Okay? Now I want you to look at the c over d in the denominator. That c over d in the denominator, the way that I can get that denominator to go away, you did this in an algebra class somewhere, is you can multiply this by the reciprocal. But if you do it to the denominator of this big fraction, you have to do it to the numerator of the big fraction as well. Now the reason we did this is because what does this value in red that I've circled become then? 1. So I actually have a over b times d over c divided by 1. And division by 1 doesn't change anything, right? Just like multiplication by 1 doesn't. So this yields a over b times d over c. And that's exactly why this reciprocal idea works. Okay, that's what's happening here. At some point you're going to have some child ask you, well, why am I allowed to do that? And you're going to be able to show them. Maybe looking back at some notes somewhere you'll be able to show them. That's why. You probably won't use A's and B's and C's and D's. You'll use numbers, and that's fine. But this is the same property of what's going on. It will. All right, so the other thing that students sometimes really struggle with is this idea of what does it mean to divide by a fraction? Because it feels really funny, and I often get people saying, well, 6 divided by 1/2, and they'll describe something that's really division by 2. Because division by 2, what in the world does it mean to actually divide by a fraction? Well, in order to answer that question, we're going to go back to the idea of what it means to divide by a whole number. There are 2 ways to divide 6 by 2 in a diagram to support this, okay? So one way is to say, well, somebody give me an example. What does it mean to say 6 divided by 2? Let's say we have 6 cookies. I know, apparently I want some sweets today. Talked about cakes, now we're talking about cookies. 6 cookies. What would it mean to divide by 2? How could I divide by 2 picture-wise? Okay, so I've got 6 cookies. What do I need to do? Okay, so I could make 2 groups out of this, right? So that's division into 2 groups. Now that doesn't really work very well because like when I talk about my 1/2, because I talk about my 1/2, I say, okay, I need to divide it into 1/2 groups. What does a 1/2 group look like? Right? That doesn't really work very well. So I'm going to try one other way to think about this. Any other thoughts? So we could put them into groups of size 2. Right? So I could have 6 cookies. So I've got 6 in groups of size 2. If this feels a little bit familiar, it's probably because you've taken Math 1 and we talk about this in there as being another version of how to think about this division idea. So these are 6 groups in groups of size 2. That's really helpful for the idea of division by 1/2. Because imagine now what you have instead. You have 6 cookies. I'm making them big. Now I've got monster cookies. I want 6 groups. I'm sorry, 6. My 6 cookies. 6 in groups of size 1/2. My groups don't have 2 in them. My groups now have a half in them. Okay, so instead of saying size, I'm going to talk about plastic baggies. I want plastic baggies of cookies. And the number of cookies in each bag is 1/2 of a cookie. Well, how many bags of cookies am I going to have?
12.
I'm going to have 12. And visually what you're doing is you're dividing each individual cookie into halves. So I have 12 halves of cookies. That's what division by, what?
I said those poor kids.
Those poor kids. They're monster cookies, though. That's why I made them so large. They're monster cookies. So I have 12 groups. I have 12 plastic baggies of size 1/2 each. I mean, this is what I would have to do if I only had 6 cookies and 12 kids, right?
No, you need all the cookies.
I could just eat the cookies and the kids don't get any? I could. That would be an option, I suppose, yes. All right, let's see how far we can get through this idea of exponents. All right, first thing, we're going to fill these in really quickly. You guys are going to tell me what you remember. Hopefully you remember them right. If you don't, it's okay. We'll talk about how they work and why they work this way in a minute. What happens when I have, okay, first of all, a definition of exponents. If I have a raised to the n power, that means I've multiplied a together a bunch of times. How many times? N times. For any rational number a and any natural number n. Okay, so in order for sort of this description to sort of make sense, we have to be talking about a natural number. Natural numbers are your counting numbers. 1, 2, 3, 4, 5. Okay, so that's what n is up there. All right, what happens when I multiply 2 exponent expressions, a to the m times a to the n together? How do I simplify that? A to the what? It is. It's addition of those 2 exponents. Again, we're going to talk about the why in a little bit. It's addition. So then what happens on number 2 when I divide them? It's subtraction. How is 3 different than 1?
There's a parenthesis.
Right, there's parentheses. What else? Sorry, I'm hearing lots of voices all at the same time, so I'm not hearing anybody specifically. What else is different?
Like a power to a power.
This is a power to a power, whereas the first one's what?
Wait, say that again?
Becca said that this is a power to a power on number 3. Compared to number 1, what is number 1? It's 2 base numbers. That's what I wanted you to identify. On number 3, I only have 1 base. It's the base A. It's written down 1 time. And on the first one, I actually have 2 bases written down. They match, but I have them written down twice, right? Okay, so what happens on 3 then, instead of it being added? M times n, they're multiplied. 4 and 5 are very similar. They say I've got parentheses with something inside of it. I've got an exponent on the outside. So what can I do with that exponent? It looks like it's distributing. Now, it's not really what we mean by distribute, because distributing is actually something that happens over addition, and it actually wouldn't work at all with rational expressions like this with the exponents. But we have this sort of same feel to it, right, where it applies to each one of the values. And we can do the same thing on number 5. What's different between 5 and 6? It's a negative. What's that negative do? Anybody remember? It is 1 over, Becca, but it's easier to think of it the way Abby was just about to tell us what you have. Yeah, it does a reciprocal. When you have a negative exponent, it makes the reciprocal. So what's the reciprocal of a over b? B over a. So this is equivalent to having b over a raised to the m power. And then if we use the previous one, we recognize, oh, that's just b to the m over a to the m. Okay, so it flips it and it applies this sort of a distributive feel to it. Okay, I have time to show you why the first one works at least. You know what this is supposed to be. You told me that this is supposed to be we add the 2 exponents together, right? Let me show you why it works. What does a to the 3rd mean? Perfect. What does a to the 4th mean? How many a's did I end up with? There are 7 A's. How do you get from 3 and 4 to 7? You add, right? There's a concrete example that shows why that one works. Let's do the second one. We're supposed to subtract, right? Okay, so we're going to show why that worked, how that actually played out in this particular problem. So a to the fourth, you told me just a minute ago, looks like this. And a to the third looks like this. So what do? Yeah, you reduce by canceling like terms, which leaves you with a. Now, it doesn't sort of look like it, but this is a to the power of 1, right? Because there's just one of them. So how do I get from 4 and 3 to 1? You subtract.
We don't have to write the 1, do we?
No, you don't.
Okay.
No, in fact, what I'm doing on these slides right here now where I'm justifying these properties, you don't have to do any of this for me ever again. But what I want you to recognize is when some child asks you, why in the world did you add those exponents instead of multiply? You should be able to create a concrete reason very quickly to show why it works. And that's the idea.
And if it's to a negative power, I guess it's like 1.
Yes. Yeah, and we'll do that one next time. So let's stop right here.